last lecture, we were doing a separation of variables in spherical polar coordinates. This was in the context of working with del squared. So, basically we have the equation in 3 dimensions. We use spherical polar coordinates r theta phi, and typically the Schrodinger equation would become minus h cross squared by 2m del squared psi of r theta phi plus v of r, because we are considering central potentials, psi of r theta phi is E psi of r theta phi. I will recapitulate the salient features of what we did pertaining to this equation in the last lecture and then move on to new things. I will also elaborate on the separation of variables done in this context. So, essentially we wrote del squared in terms of L squared. There is a radial component which is 1 by r squared delta by delta r of r squared delta by delta r. Then there is a function of theta and phi that appear here, operator dependence on theta and phi, that can be written as minus L squared by h cross squared r squared. We had seen this in the last lecture. We explicitly wrote out del squared in spherical polars and identified L squared by h cross squared r squared to be the rest of this, the angular part. So, that gave us del L squared as minus h cross squared times 1 by sin theta delta by delta theta of sin theta delta by delta theta plus 1 by sin squared theta delta 2 by delta phi squared. So, this is the operator representation of L squared in polar coordinates, spherical polar coordinates. Clearly, if you are looking at a term like this, it would involve the action of 1 by r squared delta by delta r of r squared delta by delta r on psi and the action of L squared on psi. So, we decided to first look at L squared action on psi, but since L squared only has dependence on theta and phi, I would like to write psi as r of r, some function of theta phi, and that was further reduced to this form. So, we wrote psi of r theta phi as r of r, some function theta of theta, some other function phi of phi, and therefore, the L squared equation would simply be L squared acting on theta of theta phi of phi is lambda h cross squared theta of theta phi of phi. Now, one thing is evident. This is an eigenstate of L squared, and therefore, lambda should be of the form L times L plus 1. This is the message learnt by looking at the spin system, which had the same algebra as orbital angular momentum. The values of L, however, could get restricted compared to what we saw earlier in the case of the spin system, because in the case of the spin system, just from the algebra, from the angular momentum algebra, we realized that L could take values 0, half, 1, 3 by 2 and so on. But here, because we work in physical space, There are some inputs that go in, inputs relating to the wave function, one of them being that the wave function must be single valued at any point. That would restrict L, because to begin with it restricts M, which is the eigenvalue corresponding to Lz. In fact, we saw that M could take values only 0, plus minus 1, plus minus 2, plus minus 3, and so on. And therefore, that is going to restrict L as well. Just to recapitulate what we did, we therefore went ahead and wrote out this equation in an expanded form. So, we have 1 by sine theta delta by delta theta of sine theta delta by delta theta acting on theta of theta phi phi plus 1 by sine squared theta delta 2 by delta phi squared acting on theta of theta phi phi. There is an h cross squared there which cancels with the h cross squared here, and I pull the minus sign to that side. So, this was the eigenvalue equation that we had. Of course, it is clear that this acts only on theta and not on phi, and this operator acts only on phi and not on theta. So, I have phi of phi by sine theta delta by delta theta of sine theta delta theta by delta theta. But remember that I can now replace a partial derivative with the total derivative, because what I have here is only a function of theta. The second term gives me plus theta of theta by sine squared theta d2 phi of phi by d phi squared is minus lambda theta of theta phi of phi. This was the eigenvalue equation, and therefore, I have this equation here. Clearly, in the separation of variables, by now we know that you just divide by theta phi, and then let me write the equation on the other side. Therefore, I have 1 by sine theta, theta of theta, d by d theta of sine theta, d by d theta of theta, that is the first part, plus 1 by phi of phi sine squared theta d2 phi of phi by d phi squared is minus lambda. So, that is what I have after having divided by theta phi. We are in function space. These are not kets, these are functions of phi and functions of theta. This is a function of theta and that is a function of phi. So, such a division is warranted. I can make this better. Suppose I multiply by sine squared theta. I have the following equation. The sine squared theta disappears from here, leaving behind only a phi dependence. minus lambda sine squared theta. That is what I have. I can make this better. I can pull the lambda to this side, and therefore I will have the following equation plus lambda sine squared theta, because I have got it to this side, is minus 1 by phi of phi d2 phi of phi by d phi squared. It was here that I pointed out to you that this left hand side depends only on theta, the right hand side depends only on phi, and therefore, if these two have to be equal, each should be equal to a constant, and we decided therefore that d2 phi by d phi squared would be written as minus m squared phi. This gave us a solution. Phi of phi is e to the I m phi, normalized with the root of 2 pi, and also because the wave function is single valued. If phi changes by 2 pi, the wave function should not change. This restricted m to integer values. You will recall that Lz is minus IH cross delta by delta phi in spherical polars. Therefore, d2 phi by d phi squared is minus m squared phi of phi, implies that Lz phi of phi is mh cross phi of phi. So, delta 2 by delta phi squared, pull out the minus IH cross out here, and you get this. Not surprising that phi of phi is an eigenstate of Lz as well, because L squared and Lz commute with each other, and therefore, this object phi of phi here is a common eigenstate of L squared and Lz. The eigenvalue corresponding to Lz would be mh cross. We have to find the eigenvalue corresponding to L squared, and as I suggested, since this is lambda, and we know from earlier experience that lambda would be of the form L times L plus 1, we can now put 2 and 2 together. Since m takes values from the angular momentum algebra, I already know that m takes 2L plus 1 values for a given L, ranging from minus L to plus L. And therefore, if m is allowed only integer values, this L here should clearly take only integer values, and like any respectable L, it has to take values 0, 1, 2, 3, 4 and so on, all positive values and all positive integers and 0. So, this is a difference between orbital angular momentum and what you got for other objects that come with the angular momentum algebra, like spin or isospin, where we realized that L could take positive values 0, half and so on, and m takes values minus L to plus L, that is 2L plus 1 values in steps of 1 for a given L. Now, this restriction has come because of a very crucial input, that the wave function should be single valued in physical space, should have the same value whether we work with phi, a definite angle phi, or with phi plus 2 pi. So, that is one feature which is special to orbital angular momentum and which is worth remembering. So, now we can just go back to this equation and substitute, and then try to solve for the theta equation. So, I have sin theta by theta of theta, d by d theta of sin theta, d theta of theta by d theta, plus lambda sin squared theta is minus m squared, because we set d2 phi by d phi squared as minus m squared phi. So, this would be plus m squared. Multiply throughout by, divide by sin squared theta first. So, I have 1 by theta of theta sin theta, d by d theta of sin theta d theta by d theta, that is the first term, plus, and bring this to this side, bring everything to the left hand side. So, lambda minus m squared sin squared theta equals 0. So, let us multiply by theta of theta, and that is what I have. So, I have 1 by sin theta d by d theta of sin theta d theta by d theta plus lambda minus m squared by sin squared theta theta equals 0. If you go back to the expression for L squared, that is simply retained. I have a total derivative because I have done a separation of variables, and what I got from the phi equation gives me this. I substituted the eigenvalue corresponding to the equation for the function of phi of phi, and there was a lambda which was already there from here. That is the eigenvalue equation for L squared. That gave me the lambda, and therefore, this is the equation for theta of theta which I have to solve. So, if you look at this, just for the sake of writing things in a compact fashion, let me define cos theta as W, implies theta of theta is some P of W. I need to find out d by d theta. So, d by d theta would be d by dW times dW by d theta. That gives me a minus sin theta. So, let us just recast this equation in terms of W. This is analogous to what we did in the harmonic oscillator problem, where I just wrote had an equation in as a function of x. It was a one dimensional oscillator, and the variable was x because we were working with Cartesian coordinates, and x went from minus infinity to infinity. For convenience, we defined rho, which was alpha x, then wrote an equation for rho. It was a differential equation in rho that we solved. The variable was rho is alpha x in the context of the harmonic oscillator. Here I am just calling it W and now rewriting the equation. This would give me a d by dW, the minus sign and the sin theta cancels out. So, I just have a minus d by dW. All this gets replaced by minus d by dW. Now, this again picks up a minus sin theta. So, that gives me a minus sin squared theta, which is a minus 1 minus W squared, but there was already an overall minus sign. So, this whole thing just becomes d by dW of 1 minus W squared d by dW of P of W. So, the first term just becomes this plus lambda minus m squared by 1 minus W squared, P of W equals 0. So, this is the equation I have. As I said, this is analogous to the procedure we used when we worked with the linear harmonic oscillator. Let me quickly recapitulate what we did in the case of the harmonic oscillator. There we had an equation, a differential equation for psi of x, where I defined rho as alpha x and therefore wrote it as psi of rho. Then we examined that equation asymptotically. That means what happens when x goes to plus infinity or minus infinity, which are the limits of x. You want the equation and the wave function to be well behaved. You want the wave function to be well behaved asymptotically. So, the asymptotic form, so rho going to plus minus infinity implied that psi of rho went as e to the minus rho squared by 2. So, the Gaussian form was determined by looking at what happens when x or equivalently rho go to plus minus infinity. I do the same thing here. So, this was the linear harmonic oscillator. Now, look at this equation. W is cos theta. So, trouble comes when W squared goes to 1. This term is going to create trouble because the denominator has 1 minus W squared. So, the analog of looking at what happens when x goes to plus minus infinity in this case is to look at what happens when W squared goes to 1. So, if things have to be well behaved as W squared goes to 1, m squared p of W should go to 0 for m not equal to 0. Recall that m can take values 0, plus minus 1, plus minus 2 and so on. So, for non-negative m, I require m squared p of W to go to 0 as W squared goes to 1. So, this means that p of W should go as 1 minus W squared to the alpha, where alpha is greater than 0. This statement is the analog of the statement psi of rho is goes as e to the minus rho squared by 2 for large rho. So, that is the first step in all these problems where you solve for one where you solve a differential equation, an eigenvalue problem, which involves one argument, in this case W. Therefore, I would like to write p of W as 1 minus W squared to the alpha some q of W. This is analogous to what we did there. We wrote psi of rho as e to the minus rho squared by 2 times some function of rho, and the behavior of this function should not affect the asymptotic form. In fact, you might recall that the differential equation for psi was then rewritten, and we had a differential equation for f of rho in that case. So, we will have to do the same kind of thing here and try to solve for q of W. Now, so my aim is to get an equation, a differential equation for q of W, and that can be simply done. I am just simply going to call 1 minus W squared to the power of alpha as f of W, and therefore, p of W is f of W q of W. I need p prime. So, p prime of W, by prime I mean the differential with respect to W, is f prime of W q of W plus f of W q prime of W. So, f prime of w is alpha 1 minus w squared to the alpha minus 1 times minus 2 alpha minus 2 w, sorry. So, this is minus 2 w alpha 1 minus w squared to the alpha minus 1. This comes from p prime of w. So, when I multiply with 1 minus w squared, as is expected here, I get a term 1 minus w squared times f prime of w. So, let us see what that gives us. 1 minus w squared f prime of w is minus 2 w alpha 1 minus w squared to the alpha, which is f of w. So, that is what I have. Now, I use all that and I get the following. I have d by dw of 1 minus w squared p prime of w, which we have got there, f prime q, just dropping the arguments for the moment, plus f q prime. That is the first term. So, let me consider that. That is d by dw 1 minus w squared f prime is what we have got here, that is minus 2 w alpha f, we have already got that there, times a q plus 1 minus w squared f q prime. So, this is the first term. And when I expand it, this just gives me minus 2 alpha f q minus 2 w alpha f prime q minus 2 w alpha f q prime minus 2 w f q prime from there, plus 1 minus w squared f prime q prime plus 1 minus w squared f q double prime. Now, since the second term, there are only two terms here, and since the second term just has p of w, no derivatives, this just has an f q here, there is neither q prime nor q double prime. It is clear that the q prime terms and the q double prime terms come from here. So, this can be just written as q double prime times 1 minus w squared f, and that is all for q double prime. Let me group the q prime terms. Remember, prime is differential with respect to w. So, I have a minus 2 w alpha f from here, minus 2 w f from there, plus 1 minus w squared f prime q prime, substitute back. So, minus 2 w alpha f q prime. So, the q prime has been pulled out, and this can be just written as minus 4 w alpha f minus 2 w f. Then I have terms which involve q. Well, there is one term here, there is one term there. So, that is a minus 2 alpha f q minus 2 w alpha f prime q. That is the contribution from the first term. So, now I can just add it all up. So, this just becomes q double prime times 1 minus w squared f. Recall that f of w was 1 minus w squared to the alpha, where alpha was greater than 0. I can write this as minus 2 w f 2 alpha plus 1 times q prime and then I have the q dependent terms From there I have minus 2 alpha f minus 2 w alpha f prime, and from here I have plus lambda f q. Remember that p was f times q, minus m squared by 1 minus w squared f q. This is equal to 0. So what does that mean? Q double prime times 1 minus w squared f minus 2 w f 2 alpha plus 1 q prime, and now group the q terms. There is a lambda, so f q, if I pull that f out, that gives me a lambda minus m squared by 1 minus w squared. So that is already there. And then I have a minus 2 alpha f q and a minus 2 w alpha f prime q equals 0. But you see, once I substitute for f prime as minus 2 w alpha 1 minus w squared to the power of alpha minus 1, I can rewrite this equation cancelling f on all sides. This can be written as this object f prime, which is this, can also be written as minus 2 w alpha f by 1 minus w squared. And therefore, the equation takes on a very nice form. You can cancel f everywhere, and the equation simply becomes simplified form 1 minus w squared d2q of w by dw squared. That is the first term, minus 2w times 2 alpha plus 1 dq by dw. That is the second term, plus lambda minus 4 alpha squared minus 2 alpha plus 4 alpha squared minus m squared by 1 minus w squared q equals 0. Just added a 4 alpha squared and subtracted out an extra piece in order to get this term. So that is what I have, and as you can see, trouble comes when w squared is equal to 1. As w squared approaches 1, this term is going to give trouble unless 4 alpha squared equals m squared. You will recall that p was written as one minus w squared to the power of alpha q of w. So now you see we are fixing the value of alpha. How does the value of alpha get fixed? Because you don't want a problem as w squared goes to 1. So it's always the fact that the wave function is single valued at a point, or that the wave function should be well behaved. These are the properties of the wave function, very important properties of the wave function, as you can see, because they help you fix the behavior of the eigenfunction. But alpha is greater than 0. It has to be greater than 0. Otherwise, you would have had trouble. Therefore, alpha, 2 alpha is equal to mod m, because m can take values, integer values, positive, negative, and of course 0. So I get this very important result that alpha is mod m by 2. So look at p of w. It's 1 minus w squared to the mod m by 2 times q of w. So, this is the analog of this problem. I have already recast the equation in terms of q of w. That is the analog of what you did in the case of the linear harmonic oscillator, where you recast the differential equation to a differential equation in terms of f of rho. And then what did you do? You solved for f of rho. How did you solve for f of rho? You start with a series solution. So, here too we will now assume a series solution, some sigma to infinity Cs w to the s, where C sub s are the coefficients. As in the case of the harmonic oscillator, we have to find out what are the coefficients that survive. To begin with, of course, I would imagine that this is an infinite sequence. I will substitute for q of w in this differential equation and see what it gives me. Same way that we did for the oscillator problem, except that we are doing it now for an angular wave function, but the procedure is the same. So, when I substitute there, dq by dw is summation over s Cs s times s minus 1 w to the s minus 1, and d2q by dw squared summation over s Cs s times w to the s minus 1, and here it is s times s minus 1 w to the s minus 2. Now, when I substitute back there, I have a term 1 minus w squared times d2q by dw squared. So, the first term 1 times this gives me the following, and then minus w squared times this will give me a power w to the s. This would give me a power w to the s, because dq by dw comes with the power w to the s minus 1. And then, of course, I have all these terms, but this term drops out because 4 alpha squared is equal to m squared, and therefore, I just have this time summation over s Cs w to the s equals 0. So, let us look at the lowest order w to the s minus 2, and s went all the way from some value sigma to infinity. We are supposed to determine sigma. In a series expansion of this kind, you know that these behave like basis functions, and that is precisely why we are expanding it in this fashion. So, you have to equate each power of w to 0, and since this is the only contribution to w to s minus 2, let us first start with s equals sigma. So, that tells me c sigma times sigma minus 1 equals 0. But c sigma is not 0, because you have written the series as summation s is equal to sigma to infinity Cs w to the s, and the lowest non-zero contribution comes from sigma. Since c sigma is not 0, sigma is 0 or 1. So, this series starts from s is equal to 0, and s takes only positive integer values. This becomes an important thing, implies s takes values 0, 1, 2, 3 and so on. This is the equation which this is for small s. Now, for all other values of s, because coefficient is w to the s, for all other values of s, we can again equate the coefficient to be 0, and as in the case of the oscillator, we can get a recursion relation. I leave it to you as an exercise to show now that Cs plus 2 by Cs is minus of lambda minus s plus 2 alpha times s plus 2 alpha plus 1 all of it divided by s plus 1 times s plus 2. You see, now let's find out what happens for large S. For large S, this simply goes as 1, because you have an s squared out there and an s squared out here, and therefore it goes as 1. Now that's bad news, because it means that all contributions are equally important, and you cannot truncate the series at some Cs. In fact, this is the kind of ratio of coefficients that you get in the series expansion for 1 minus w squared to the minus 2 alpha, because there you will find that if you expanded the series and took a ratio like this, it would go as 1. And that's bad news, because then P of w is 1 minus w squared to the power of alpha by 1 minus w squared to the minus 2 alpha to 2 alpha. I have brought the minus 2 alpha down, and that goes as 1 minus w squared to the alpha. That's bad news, because when w squared is equal to 1, the term is going to blow up. Now the only way to avoid a situation like this is to do precisely the kind of thing we did in an analogous situation in the case of the harmonic oscillator. You have to truncate the series. Now truncating the series would mean the following: for some s, Cs plus 2 by Cs should go to 0. In other words, suppose I fix lambda to be t plus 2 alpha times t plus 2 alpha plus 1, where t is an integer. So let's start with the 1, 2, 3 and so on. When s is equal to t, it is clear that the numerator vanishes, and therefore the series will truncate, because beyond that there is no ratio of coefficients worth talking about. This is precisely the kind of thing we did with the recursion relation for in the case of the linear harmonic oscillator, and it was this truncation of series which gave us a differential equation which had the Hermite polynomial as a solution. So that is how that special function, the Hermite polynomial, came into the picture. It also brought in a quantum number, because in the case of the oscillator it brought in the quantum number n, and we had Hn of rho or Hn of x. We would expect something like that to happen in this case as well. Set lambda equal to this value, the series will truncate. Check to see if the differential equation now, once the series truncates, is a familiar differential equation, in the sense it has some special function as a solution, and indeed that is what we will get. We will also have a quantum number coming up in the process. So it is a standard ploy that I employ in the case of the linear harmonic oscillator, in angular momentum algebra and so on, when I am looking out for series solutions. Choose lambda to be t plus 2 alpha times t plus 2 alpha plus 1, where t is 0 or a positive integer. Then the series terminates when s takes the value t, Cs plus 2 becomes 0, and because Cs plus 2 is 0, Cs plus 4, Cs plus 6 etc. are 0, because the same recursion relation holds. In the next stage you will have Cs plus 4 is something times Cs plus 2. and since Cs plus 2 is 0, all of them are 0. Set Cs minus 1 also, Cs plus 1 also to be 0, because you want to truncate the series. Then by the recursion relation, Cs minus 1, Cs minus 3, they are all 0. So depending on whether the series terminates with Cs when S takes the value t, and the important thing is this, it is not just a finite series. If S is even, it is an even integer, only even objects contribute, like C0, C2, C4, C6 and so on, as you can see. If S is odd, C1, C3, C5 and so on contribute. So that is the structure, and you have terminated the series. But this gives you the value of lambda, because 2 alpha is mod m. So lambda is t plus mod m times t plus mod m plus 1, and I would call this L, and I would therefore call this L plus 1, and t takes value 0, 1, 2, 3 etc. Mod m takes value 0, 1, 2, 3 etc. The L takes values 0, 1, 2, 3 etc. So the fact that the asymptotic behavior in the case of the oscillator, that means x going to plus minus infinity, and here omega squared, w squared going to 1, that means theta taking values 0 or pi, because cos theta was w. The fact that the wave function must be well behaved when these limits are reached by the argument, that is what has quantized the eigenvalue. Quantization of m came because you expected the wave function to be single valued. Quantization of L has come because you truncated the series, because the asymptotic behavior should not be jeopardized. So it is really the well behaved nature of the wave function, the single valued nature of the wave function, that gives you quantization. Returning now to this problem, so I have lambda equals L times L plus 1. So I can go back to the equation for Q and see what I have. The equation for Q simply said this: minus 2w times 2 alpha plus 1 dq by dw plus q times lambda minus 4 alpha squared minus 2 alpha plus 4 alpha squared minus m squared by 1 minus w squared, and that term dropped out, is equal to 0. So in terms of m, which is what I will write now, I have d2q of w by dw squared minus 2w 2 alpha plus 1 dq by dw plus lambda is L times L plus 1 minus 4 alpha squared is mod m squared, 2 alpha is mod m, q is equal to 0, q of w. Let us see what q can be. It is clear that since w is cos theta, we are now looking for an expansion for q of w in terms of an orthonormal basis set of functions which are functions of theta. Okay, in that term with 2 alpha plus 1, there too set 2 alpha equals mod m. Everything has to be written in terms of mod m. Further, if m is 0, for m equals 0 we have 1 minus w squared d2q of w by dw squared minus 2w times 2 alpha plus 1 dq of w by dw plus L times L plus 1 q of w equals 0. But this is precisely the equation corresponding to the Legendre polynomial. The Legendre polynomial, usually referred to as P of w, where w is cos theta, PL of w, that is a Legendre polynomial that satisfies precisely this equation. So, PL of w is the same as q of w if m equals 0. Now, if m is non-zero, I would therefore suspect that the equation for q of w would be that of the associated Legendre polynomials, because they come with another number PLM, another quantum number. So, I have another quantum number m. So, I have two numbers associated with this. This is the associated Legendre polynomial. And they are defined in terms of PL of w as 1 minus w squared to the m by 2 dm by dw, the mth differential of PL of w. Of course, I can define it also for, this is for m greater than 0, and I can define it for m less than 0 simply. If m is less than 0, it is minus 1 to the m L plus m factorial by L minus m factorial P L m mod m of w. This is for m less than 0. Now, if you identify your q of w in the following fashion, you identify q of w as the mth differential dw to the m of PL of w as q of w. Then you can check for yourself, and I leave it as an exercise, that the equation for q of w for m not 0 is precisely the equation satisfied by the associated Legendre polynomials. But these polynomials have a normalization property which says PLM of w, PL prime m of w dw. Remember, the w goes from minus 1 to 1. It is not delta LL prime. It is 2 by 2L plus 1 L plus m factorial by L minus m factorial delta LL prime. And therefore, what I need are orthogonal polynomials. I define a theta Lm of theta, which is of course PLM of cos theta. But in order to have the normalization straight, this would be root of 2L plus 1 by 2, root of L minus m factorial by L plus m factorial, PLM of cos theta. Then it is clear that integral theta Lm of theta, theta L prime m of theta, sin theta d theta, because that is d cos theta, theta itself going from 0 to pi is delta LL prime. So, finally, I have the wave function. The wave function is given by theta of theta, phi of phi, and that is simply theta Lm of theta defined here, so that it is normalized to 1, e to the im phi by root 2 pi, so that phi of phi is also normalized to 1. And this object theta Lm of theta e to the im phi by root 2 pi is referred to as the spherical harmonics Ylm of theta phi. So, these are in fact the angular wave functions. L squared y L m of theta phi is L times L plus 1 h cross squared y L m of theta phi. Instead of lambda h cross squared, I have this, and L z y L m of theta phi is m h cross y L m of theta phi. The y L m of theta phi have some very interesting properties, particularly with reference to parity, and I will elaborate on that in my next lecture.